In this video I will discuss several extensions of the lasso. The first is the so-called adaptive lasso, which is designed to counter the tendency that the lasso has to select too many variables. So you will often see if you run the lasso, you'll get still quite a lot of variables selected, some with relatively small coefficients. As we'll see later on in the theory, we can also explain that theoretically. This may not always be a good thing, in particular if you're interested in variable selection and want to have a sparse model and you have few selected variables. So the adaptive lasso is designed to counter this. So the objective function that we minimize looks like this. It looks very similar to the regular lasso. The only difference is we have a wj here in front of the beta j. This wj is a weight which can change, and that is crucial depending on which parameter it's attached to, which j. In particular, what we do is, suppose we have some initial estimator of beta j, then we let our weight depend on the inverse of some power of that. The idea being that if your initial estimator shows a large coefficient, so this would be an important variable, you give it a low weight because 1 over something large will become small. And so the penalty for that particular variable will become small. On the other hand, if you are close to 0 with your initial estimator, it seems that this variable might not be very important, then doing 1 over that would make this a large weight. So you put a heavy penalty on this particular coefficient. And it will be likely set to 0 then in the second step. So it's a two-step estimator. The first step is, say, an initial screening, giving an indication of which variables are relevant and which ones are not. And then with that information, we do the lasso in a second step, but already having information about which are the most important variables and which ones are actually have coefficients close to 0. Of course, what is crucial is how do we get this initial estimator? Well, one thing you could do is just least squares, although it only works obviously if p is smaller than n and should be quite a bit smaller than n. Well, you could do rich regression, that we can always do, and you could even do lasso first. So you would do actually the same thing as here, except just setting these weights equal to 1. That is the regular lasso. Of course, then you run into problems that you have some variables which get already kicked out. So some coefficients will be set to 0. And then, of course, it will not work to do 1 over the estimator. So in that case, what we simply do is we take a very small number, say some small epsilon, 0.00001, and set our initial estimator equal to that, such that we just make sure that we really give it a very large penalty, such that everything that was 0 in the first step will also be 0 in the second step. This two-step procedure then has two effects. We will delete more irrelevant variables, simply because we do it through the weight here, and as an added benefit, we'll actually have less bias because, well, given that this weight is sort of taking over the role of the tuning parameter lambda here, we can actually have less bias on the relevant variables. So it's a twofold thing, and we actually gain two things. Note that I added here a superscript nu on my weight, on the absolute value of the initial estimator. The idea of that is that you, by choosing this larger or smaller, you can vary how strongly you want to put a penalty based on the initial step. So a standard approach would just say to take nu equal to 1, but if that's not strong enough, you could go higher and take it equal to 2, or if you think it's too strong, you could make it lower and say it equal to half. Okay, so let's analyze what happens with this adaptive lasso. So we're going back to our orthogonal design because we can do things explicitly there. Right, so we assume x prime x over n is equal to the identity matrix. I'm not going to write out all the first order conditions, as you can imagine, given that everything here is the same as for the regular lasso, just this wj here is multiplied by this. We get exactly the same first order conditions, except that now we have the subdifferentiable times wj. And this sj is still 1 if beta j is positive, minus 1 if beta j is negative, and in the interval minus 1 to 1 if beta j is 0. So we can do exactly the same steps as we did for the lasso. We write out all these cases, and we get this solution, which actually looks very similar. The only thing that's different is that we get this multiplicative effect of these wj's here. Now, remember that we could write in the orthogonal design case, we could write the least squares estimator as just x prime y over n. So we can actually also write the adaptive lasso as a soft thresholding kind of estimator as a function of the least squares estimator. So we're again going to, if the least squares estimator, right, which is of course for element j, it's just xj prime y. If that is not far enough away from 0, given by this condition, we'll set our estimator equal to 0. If it is far enough away, we don't set it equal to 0, but we do move it towards 0. We shrink it towards 0 with this amount here, or this amount for the negative case. But of course, the difference with the previous case is that now we have this wj, which affects how strong is my penalty here, how strong is my condition for putting it equal to 0, and how strong is my bias here. So let's take, because we can do that in the orthogonal design case, let's take our weight to be 1 over the least squares estimator. Because then we'll actually see some things will start cancelling out, and we'll see how this adaptive lasso works. So we take it 1 over the absolute value of beta hat OLSJ to the power nu. I'll plug that in. If we go back one slide, I plug that in here. Then I get, of course, just this expression here. But now, of course, we see, because we actually took the OLS estimator, so we have now the same estimator here as we have here, as we have here. So we can define this whole thing as a function of the OLS estimator. And actually, this is another thresholding estimator. So we can define say a generalized soft thresholding estimator having this form here, where if we take nu equal to 0, we just retrieve the regular soft thresholding, the regular lasso estimator. If we increase nu, we get a stronger effect based on the initial thresholding. And common values, as I already mentioned, are nu equal to 1 or sometimes nu equal to 2. Now we can again make a graph and look at what happens here. So we have the same plot as we had for the lasso. So the lasso is still here, the blue line. But we also now add the lines for the adaptive lasso. So we take nu equal to 1, nu equal to 2. So the dotted line is nu equal to 1, and the green dashed line is nu equal to 2. And well, we see that setting to 0 here actually happens in the same range. As we will see later, it depends on the value of lambda, that's the case. But what we also see here is that even though here there's no effect on when we set our estimator to 0, there is clearly a difference when we look at the bias, the shrinkage. So the larger your least squares estimator gets, the less you shrink. Because we were moving back towards the 45-degree line of the least squares estimator. So the lasso always has this shrinkage. It always moves down lambda over 2 from the red line. But for the adaptive lasso, it depends on how big the OLS estimator is. And of course, this makes sense if we go back to the formula, right? The larger your OLS estimator is, the smaller this part, the shrinkage, will be. So now we look at a smaller value of lambda. And this is the situation that we typically encounter in practice. So here, for this lambda, we see that the lasso only sets our estimator equal to 0 in this range when beta hat OLS is in small range, whereas the adaptive lasso sets the estimator equal to 0 for larger values of beta hat OLS. It depends, of course, on the value of nu, how large it is. For the bias effect, we still see the same thing. The shrinkage becomes less if your estimator becomes larger. So in this case, if we take a lambda like this, we get a situation where we would get more coefficients set to 0 with the adaptive lasso than with the regular lasso. And this, of course, is exactly what you typically observe in practice, and also what actually the whole goal is of the adaptive lasso. Now we can also do the opposite. Let's take a very large lambda. Now we see that for this very large lambda, actually, the adaptive lasso sets fewer variables to 0 than the regular lasso. And so the regular lasso goes all the way, everything up to a lambda over 2 here. The adaptive lasso sooner realizes that actually this beta hat OLS is still pretty big, so we should not set it to 0 anymore. And so this is an interesting find that actually what the adaptive lasso is doing is not just being more strict. It's actually being more robust against getting your lambda wrong. So here you made your lambda way too large. And your adaptive lasso would say, well, wait a minute, your lambda is so large, but if I do my initial estimation, I get such a large beta at OLS, I should override that lambda. So it provides also some stabilization against getting your tuning parameter lambda selected wrong. So based on the two things we mentioned before, what we always see is the smaller bias, and what we sometimes see, depending on the choice of lambda, is more or larger or smaller coefficient being set to 0. And of course we can just calculate that. We can calculate the boundary point, because we know, well, this is the condition when exactly when the adaptive lasso will start setting things to 0, so you can see how large your X or how small your X should be, and it will have this value. What we know for the regular lasso is that value is just lambda over 2. That's what we already calculated before, and we can simply check when is lambda over 2 smaller than lambda over 2 to the power 1 over 1 plus nu. Well, in this case it will be if lambda over 2 is smaller or equal to 1. So the value of 1 here is not particularly important. After all, it really depends on how you code lambda, right? Because we use this 2, but some people divide everything by 2, and then of course you would not get 1, but you would get 2. Now in practice this does not seem to matter so much, because in practice what we do observe is really it does set more coefficients to 0. But I think it's good to know that you have some stabilization, at least in theory, some protection against putting your penalty too large. And of course also putting it too small. Now when we talk about stability, we can also talk about a different kind of stability. And that is another feature of the lasso. So it does not only select too many variables, it also tends to select variables in a quite unstable way. In particular, if the columns of X are highly correlated. So if the regressions have highly correlation. And what it then does, if you have these highly correlated variables, the lasso tends just to select one of them. And as we'll see, you could almost argue that it does so almost at random. Now, in a way, this makes sense from a prediction point of view, because if all these variables are so much alike, well, you're not so much worse off if you include the wrong one, but one that is very alike the right one. And the reason why it happens for the lasso is that the objective function is convex, but it's not strictly convex due to the absolute value. So what the elastic net is trying to do about that is by saying, well, why don't we don't just add a lasso penalty, the L1 penalty, but we also add an L2 penalty or squared L2 penalty here. So this is a ridge penalty. So you do lasso penalty plus ridge penalty. And yet, of course, each gets its own tuning parameter. And this creates strict convexity because now we get away from this L1 norm. L2 is strictly convex. And as a consequence, this one will always have a unique minimum. We know that if the objective function is convex, there is of course a global minimum. So the value of the objective function is only one global minimum, but there could be the minimum does not have to be unique in beta. And that's what we see, that it very quickly tends to switch between betas which give you almost the same minimum. So the ridge is much less sensitive to that. And instead of selecting of these groups of highly correlated regressors that tending to select just one of them, it tends to select all of them together, which is the much more natural way to have. Now there is of course one issue, and that is we do double shrinkage. We do L1 shrinkage and L2 shrinkage, so you get double shrinkage from lambda 1 and from lambda 2, which means you really get a lot of bias. So what they suggest in the original paper is to, once you have the solution, to multiply it with 1 plus lambda 2, which is sort of undoing the ridge shrinkage bias. And we'll look at an exercise where we'll see why this makes sense. Now let's illustrate this graphically. I think this is the easiest way to see it. So we have the lasso, and now let's take correlated regressions. And note how flat I've drawn these contour lines. This is for a reason, because if you have correlated regressions, so here we have two regressions, and if they are correlated, suppose they would be actually the same or really just linear functions of each other, then all of these points on a straight line would give you the same value of the objective function. So here they are not identical, of course, but they are just highly correlated. But still, linear combinations, so you might swap some x1 for x2, and it hardly changes the value of your objective function, which is why in this direction it's very long, but in this direction the lines are very close to each other. And now what we see is, well, we end up with the lasso here in this point, and we select, we set beta 2 equal to 0 here. But you also see that, well, we might just as well have ended up here, right? The lines are very close to ending up on this point because they are so flat. In the earlier cases that we looked at, where we had much more, where the contour lines look much more like circles, you would end up much more clearly here. So you could imagine that if you add a few observations to your data set, the contour lines will change, so the objective function will obviously change a bit, and it might just tilt enough that instead of ending up here, we end up at this point. So we suddenly select beta 2 and set beta 1 equal to 0. And this is in fact what we see in practice. And I will show that also discuss this in a later lecture where I look at an economic application. And we see that if we, for instance, do a time series analysis and we move through time and we take every time a different subsample, we'll suddenly see that our variables that get selected change. So there is an instability. So if you add a few more observations or you delete a few observations, you suddenly end up with different variables included, which of course, in terms of interpretation, is not very nice. If you're only interested in prediction, you might not care. But if you want to give some meaning to the variables that are selected, that is of course not very nice. Now, it's really due to this shape of the L1 penalty, because we have these straight lines here. Right? This is of course the convexity, but not strict convexity. So if we add an L2 penalty, as the elastic net does. We don't have these straight lines anymore, but we have more curved lines. And so what we see now, right, we have the same shape of the contour line, still these highly correlated regressions. What we'll see now is that because there is now this bump rather than a straight line here, we'll end up somewhere in the middle where we clearly include both coefficients, and in fact we put them with coefficients which are actually close to each other. And this comes really from adding this L2 penalty here. So this means also that if we would now look at a slightly different data set and the line would tilt a bit, right, the angle would change a bit, you would still end up somewhere relatively close to where we are now. I mean, it would not necessarily be at the same spot, but you would very likely remain in this area where you actually include both of the variables. But before you would end up here at these points, it would be the lines would really have to change a lot. And so this is really this grouping effect that we see that the elastic net has. It tends in these cases to select both of the variables, and it does, and therefore it will be much more stable, because right, if you now do it over different subsamples, you'll see hopefully that indeed we include the same kind of the same variables, both variables, and rather than picking one of the two at random. Now note that because we still add this L1 penalty, we still have these sharp edges here. Right? So this is not the same as a ridge penalty, it was just a circle. We still have these non-differentiable points here on the axis, which means we still do variable selection. So variable selection is definitely still possible, and it still happens. It just will not happen in these cases with correlated regressors, where you actually also don't really want it to happen, and certainly not in the way that the Lasso does it. So this is a very nice feature of the elastic net. And another nice feature is that actually we can treat it as if it were a Lasso problem. So that means we can use the same optimization techniques as for the Lasso. So what they show in the paper is that what we do is we define an artificial data set where we add zeros, p zeros below y, and we add the identity matrix scaled by the lambdas below x. And then we solve this Lasso problem, and if we then multiply the solution by that thing by the square root of 1 plus lambda 2, we get our naive elastic net solution. And that means that you don't even, although of course in packages like GLMNet, the elastic net can be calculated directly, but you would not even have to do it, because you could, as long as you could calculate the Lasso, you could build these y star and x star data sets and then just use those to find the solution for the Lasso problem and then transform it into the elastic net problem. Now there's another interesting side effect that we have here. I have not really discussed it before, but what we'll see, and we'll also see that when we look at computing the Lasso, is that actually the Lasso cannot select more than n variables, which in a way is also not, I think, not such a big deal. If you have n observations and you have more than n, you have p regressors, the Lasso will not select more than n, which I think in itself is actually okay. But there might be cases where you would want to allow to select more. But the ridge, of course, always selects all regressors, all p, so the ridge by construction always does more. Now ElasticNet can also do more than n regressors, which you can see from this formulation, because in this artificial data set, we have n plus p observations, which means it could select theoretically up to n plus p variables. Of course, we only have p regressors, and p is smaller than n plus p. So it can select all up to p regressors, unlike the Lasso. Now, to show that this is indeed the case, I very briefly, I invite you to study it yourself, but I very briefly go over the steps, which is basically just a bit of manipulation. So we write out, let me go back to the objective function. of the elastic net here, we write out the objective function, we write out the norms. So this is the squared L2 norm, the inner product. We do the same here. And we note that we have beta prime something beta. And here we have beta prime something, identity matrix, beta. So we put this together in one part. And now what we can now do, and that of course is a step that is hard. It's easy to show from this step to the top one, but hard to go from here to there. But if you go from here to there, you'll see that this thing is the same. So we have x prime x, and then we have square root lambda times identity prime square root lambda times identity. Of course, identity prime identity matrix is just the identity matrix that we have here. Right, so by extending our regressor matrix, we can create this. But of course, if we extend our regressor matrix here, we should also do it here because there's also an x here. So we also do it there, but here we don't want this part. Well, the only way to not have this part here when we do the inner product with y is to extend y with zeros. So we extend y with zeros, and then this part here will be unaffected. Well, the same, of course, here when we do y prime y, you just get 0 prime 0, which is 0. And now we see that this starts to look again like a Lasso problem. We can put this back into the norm, the L2 norm, which is now the L2 norm of the extended vector and the extended matrix times beta plus the L1 penalty. And now what they do in the paper is they add additional scaling here to reach the objective function that they describe. Now another extension that we can do, and this is actually a very simple one, is so-called post-Lasso. If we're happy with the variables we selected, but we're not happy with the bias of the Lasso, then what we can simply do is just take the variables that were selected and do OLS on them. Right? So yeah, you might start off with 100 variables, you do the Lasso, 8 of them are left, well you can then just do least squares only on these 8. And this is called post-Lasso. It's a very simple procedure, I think also a very natural procedure. And so what we are doing is just saying, okay, define the set of variables that are relevant, the ones that are retained by the Lasso, select only those and do least squares. And this very simple, slightly silly procedure actually turns out to have excellent properties and indeed helps you to get rid of the bias. So if you're worried about bias, this is often a good thing to just make your estimator a little bit nicer. Final extension that I want to mention is the group Lasso. And the group Lasso is an extension which deals with group structure. So group structure are basically variables that belong to each other. And this, of course, is something that you as a researcher have to define. And it will not always be the case that it's there. But there might be many cases where actually theory, whether that's statistical theory or economic theory or whatever your application is, tells you that groups belong together. For instance, take a time series model. Say a model where you have multiple variables, and for each of these variables you have multiple lags. Well, you might say, well, I want to treat all of the lags of one particular variable together as one group. And I want to do the Lasso in such a way that either I keep all of the variables in the group or I kick them all out. So you want to avoid a situation where from variable A you keep the first and the third lag, and from variable B you keep just the second lag, and from variable C you keep just the fourth lag. Instead you say, no, I find it much clearer, much more interpretable if I would keep all of the 4 lags from variable A and maybe none of the lags of variable B, and so on. Now this we can also do with the Lasso, but then we call it the group Lasso when we extend that. So we define groups, say group 1 up to group J, G1 up to J, where of course you your groups, the union of your groups, to cover the whole set of variables. And typically what we want is that the groups are not overlapping. So they have an empty intersection. Although you can actually also make a group Lasso with overlapping groups, but it's a bit more complicated then. Now, we can then do in exactly the same way with these subscripts. Just say, okay, beta gj is actually that subset of the betas corresponding to group j, to those beta j's where j is in gj. And then the group Lasso has a very similar formulation as the regular Lasso, but instead of taking absolute values of the betas, we sum over all the groups, and for each of the groups we calculate the L2 norm. Now, you may or may not want to multiply with some mj, which can be used to balance groups if they are unequally sized. You can imagine, of course, if you have a group which is very large, it might get distorted compared to a group which is small, because of course the penalties are different, and you could use this mj to compensate for that, but people disagree about whether this is a good approach or not. Now, note that we have the L2 norm here, and you might wonder, why don't we have the L1 norm? What's the Lasso, not the L1? Right, so you could put this one. I mean, for sure you could do that, but think about what then you actually get here. So I'm not going to answer that question because it's one of the exercises, but think about what we would get. Same thing, why do we have L2 and not L2 squared, as in rich? So again, note what you get when you would do that. And so what this penalty does, this L2 penalty, is it ensures that we have sparsity between groups. So groups are selected or are not selected, but within a group, every variable is indeed selected. Now you could actually add an L1 penalty on the whole vector, in which case you would have a sparse group Lasso where you do select groups, but it also allows you to kick out variables from within a group. So that would be another variation that people sometimes consider. That brings me to the end of this lecture on extensions of the Lasso. So what the next lecture is going to be is we start looking at the theory behind the Lasso, and we'll have a quick overview there of some important results.